Okay, good morning, and start by thanking the organizers for the invitation to present some of our work in this meeting. The work that I'll be talking about is very different from what you just heard before. It's all in numerical work. It's on a system that has become quite popular these days. It's called active systems. So I'll be talking about some glossy behavior or similar things, jamming, etc., in dense active systems. This work was carried out mostly by these two people. Shuman was a postdoc here at ICTS, and this is actually a project student, MSc student, who is doing a project with me. So some of the numerical results he has obtained, I'll present today. And these two are colleagues, Pinaki and Madan. I don't know whether they're here already or they're supposed to be here in this meeting. So this is a one-slide introduction to active systems. Basically, we are looking at systems where the objects which constitute the system, they experience basically active forces. So object can convert stored energy or ambient energy into systematic motion, so they can move by themselves. That basically makes the system out of equilibrium. And one is interested in collective behavior of systems like that, where you have a collection of active objects, which are mostly comes from biology. The examples mostly come from biology, or these are actually live objects. But nowadays, there are lots of experiments where people are working with synthetic active matter, which are not live objects, but still they have this property that they can move by themselves. And there are various complex non-equilibrium collective behavior that these systems exhibit, which has been of interest to many people over the last 15 years or so. What we are interested in is basically the behavior of such systems in the limit where they're dense, because we're interested in glossy behavior and jamming in such active systems. Again, glass transition, of course, is a subject of much interest that we heard about in the previous lecture. Nowadays, there are now experiments that are going on which basically address similar questions for a collection of active objects. I've just listed here several such experimentally studied systems where people have spent a lot of time trying to understand experimentally, and also now people are trying to develop some theories based on simulations and things like that. So that is basically the motivation for carrying out, trying to understand some aspects of active systems when they're dense, and try to find out, for example, how activity affects glossy behavior, glass transition, jamming, etc., in such systems. Just give you one example of such an experiment that is very recent, where they are looking at basically glossy behavior in a collection of bacteria, and one has this divergence of timescales, or apparent divergence of timescales, that is characteristic of glossy behavior in ordinary non-active systems. So we have been looking at various models of dense active materials, and to get kind of glossy behavior, we typically deal with not one component systems, but a mixture of two different components with different interaction parameters. That is very common in studies of glasses, and here also we basically look at similar models, but then introduce activity and try to find out how the behavior is modified. So in all of these models, so this is a cartoon where you have two different kinds of particles, and they're dense, sort of very close to, almost touching each other. And each of these particles will have an arrow on it, which denotes this active force, the self-propulsion force acting on that particle, in addition to the interparticle forces. And this self-propulsion forces will be characterized in terms of two parameters. One is, of course, the magnitude of these forces. The other is what is called persistence time. So typically in models of active matter, this self-propelling forces, they are not always in the same direction. They have their own dynamics. There's a time scale associated with how quickly the direction of the self-propelled force changes, and that time scale is called persistence time. So basically, we'll be looking at activity characterized by these two parameters. And of course, there are other parameters like density, etc., concentration, etc., which will characterize the original two-component particle system that we are looking at. So this is the kind of dynamics that we assume. As I said, we look at basically a mixture of two different kinds of particles to avoid crystallization and to, in some sense, study glassy behavior over relatively long time scales. The model that we'll be looking at is basically one of the well-known models that have been studied in the context of glassy behavior in passive systems. And the dynamics is quite simple. It's basically Landrova dynamics. You have a force on each particle. The left-hand side, of course, is mass times acceleration. And you have a frictional force. And then you have forces coming from the interaction of this particle with the other particles. And then on top of that, I add this active force, which will come with magnitude F. We assume that the active force has the same magnitude for all the particles. And this is a two-dimensional system. Direction is represented by this unit vector. And unit vector, of course, will have some angle in 2 dimensions. Just one angle is sufficient to specify its orientation. And one assumes some kind of simple dynamics, where there is a persistence time that tells you about how quickly the direction of this n is changing as a function of time. So this is basically the model, and actually what I'm going to talk about today, I'll even make it simpler by assuming that this persistence time has become very large. So we'll be looking at the limit in which the persistence time goes to infinity, which basically means the active forces on the different particles, once they're assigned, they do not change further as a function of time. Why do we look at it, this limit? Because, I mean, earlier we have done some studies where we look at these two variables, the magnitude and the persistence time, and look at dynamics of the system in different regimes. And one finds different kinds of sort of phases of the system. One has a usual liquid, one has a dynamically arrested phase, which typically one calls the glass. And then there are intermittent phases and so on and so forth. So this was done some time ago, so I'll not really go into the details of this phase diagram. But in the same work, it was pointed out that in the limit of tau p going to infinity along this axis, there is a special value of the active force such that it separates a liquid state from a jam state. So there are these two sort of phases of the system. When the active force is bigger than certain value, the system sort of behaves like a liquid. When it is less than that value, then it basically gets stuck into a jammed configuration. And one wants to basically tries to, what we have been doing the last year or so, to try to understand the behavior along this line. And in particular, today, actually, I'll be talking about only the liquid phase. So one has the limit tau p going to infinity, and one has the value of f, which is near 3 above this line, above this point. So the system is in a liquid state. And what I want to sort of tell you today is that that liquid is very unusual liquid in the sense that it exhibits many kind of phenomena, many kind of properties, which one doesn't see in a standard thermal liquid. So this just shows that, if the active force is large, then you have this kinetic energy fluctuations as you would have in a liquid. But if the active force is small, then it gets stuck into jam state. And this is athermal dynamics. So there is no thermal fluctuation. So when it gets stuck, it basically really stuck, and the kinetic energy goes to 0. But what we are interested in today is basically the behavior of this state, F equals 3, where the system particles are moving and the system looks like a liquid, but this liquid is very different from the liquid that you have in thermal systems. So I'll just again sort of reiterate what is the system that I'll be talking about for the rest of the talk. It's basically a very simple system. It's a system of particles which are interacting with each other through simple sort of Lennard-Jones type interactions. But in addition to that, there is an external force acting on each of these particles. And this force doesn't change as a function of time. So it's basically a standard system of particles which have this added complication that there are these external forces acting on these particles. These forces are in random directions, but once you specify the force on a particular particle, that force doesn't change further as a function of time. And we'll also assume that there is no thermal noise. So it's actually, in some sense, very simple system, but we'll see as we go along that there are many properties of this system that are quite different from what one finds in standard thermal liquids. So this is one of these properties. One looks at the equal time correlation function between velocities at two different points in space. So one is looking at the spatial correlation function of the velocity field. Each particle will have liquid, they will have some velocity. So one is just looking at how the velocity of one particle is correlated with the velocity of some other particle, which is at some distance r, and it's equal time correlation. And one finds that this correlation actually, this correlation persists for fairly large values of the separation between the two particles. So, of course, in this correlation function eventually goes to 0, or actually it becomes negative at very large distances because we have a conservation law. But you can see that the correlations extend over fairly large distances. And not only that, here we have plotted the correlations for different system sizes. And as the system size goes up, the range of these correlations also is going up. So the correlation function, if we want to associate some correlation length with it, then the characteristic length scale is going to increase as you go to bigger and bigger systems. And surprisingly, what we find is that this correlation length actually grows as a power law of the number of particles, and the power is very close to half, which basically means two-dimensional system. So square root of n is basically the size of the system, linear size of the system. So the correlation length is proportional to the system size. And this, I mean, if this behavior continues, then in a very large system size limit, the correlation length, of course, will diverge in the thermodynamic limit. And so the system will be something like a critical system in the sense that the correlation length actually goes to infinity in the thermodynamic limit. So, I mean, this is, of course, very different from ordinary liquids, but the velocity, spatial correlation function of the velocity is very short range. So the fact that this liquid has been made liquid by active forces, not by thermal forces, this actually makes the liquid, its character extremely different from what you know when you sort of take a substance and melt it, go into the liquid through thermal excitations. So this is one of the first unusual property. It's actually not very unexpected because this kind of systems for large but finite persistence time has been analyzed approximately or also numerically by various people earlier. And what they pointed out is that this length scale for those systems where tau p is large but finite goes at the square root of that. So here you are looking at tau p going to infinity limit. So in some sense, you know, if we extrapolate this to very large values of tau p, then again I'll find something that will diverge in the thermodynamic limit. So the velocities are correlated over space. If I look at the active forces, they also have this kind of long-range correlations. So again, when you're looking at the basically two-point correlation function of the active force as a function of distance, and as you go to larger distances, it of course goes to 0, but the length scale increases as you go to bigger systems. And here also, we find that the length scale as a function of number of particles basically has, again, a power law with an exponent which is close to half, which basically says that this length scale is proportional to the linear size of the system. So we have this process. I mean, this is something that is written in the next slide. This represents some kind of a self-organization of the velocities and self-propulsion forces, in the sense that when the system is started, the velocities are given random directions. Self-propulsion forces are also given random directions. But through the dynamics of the system, going into a state where both the velocities and the self-propulsion forces are becoming correlated over longer and longer distances. And not just that, the correlation length associated with these spatial correlations, that seems to go to infinity in the large system size limit. So it is a sort of somewhat strange kind of self-organization, which the system basically is developing through its own dynamics. So we have looked at various properties of this self-organized state. Self-organized state basically means that the velocities are correlated over long distances. Same thing about the forces. So there are these swirls, and the swirls, basically particles are moving in swirls, and the size of these swirls typically will be proportional to the size of the system. So what is the geometry of these swirls? That is something that this project student that I have now, he has looked at from his simulations, and there are some interesting things that come out of that. So here, what we are looking at is basically a color plot of this velocity correlation function, 2-point correlation function of the velocity as a function of distance. But now we are not plotting just as a function of distance, but as a function of direction also. And you can see that this color plot tells you about the correlations are strong here, and then as you go away from the center or larger distances, the correlations fall off. But these contours of constant correlation, they are not circles. They have this anisotropy. And the anisotropy here is pointing in the y direction. I mean, if we call the vertical direction the y direction, if we look at another run, same kind of steady state, then we'll find out the correlations are larger along the x-axis and so on. So they have this anisotropy. And this anisotropy is something that is characteristic of the steady state that the system reaches in a long time limit when you have this forces, when you have this constant forces acting on the individual particles in addition to the interparticle forces. So we try to analyze basically the degree of this anisotropy. And it is, of course, I mean, one can also look at the actual flow pattern, and we take this same configuration as we had plotted in the previous slide. But if you look at the actual velocities of the particles, here, I don't know to what extent this is visible, but you can see that this large arrows corresponds to particles which have relatively large velocities. And here, you can see that majority of them are pointing up. And on this side, you will see that nearly all of them are pointing down. It's periodic boundary conditions, so this connects with that. So it's basically, it seems that there are sort of two major streams of particles which are moving in opposite directions. So the self-organization is not just, everything sort of moves at random, but of course it doesn't move at random because we have these large spatial correlations. But these correlations seem to come from having two groups of particles which seem to move in opposite directions. Of course, the net velocity is 0, and et cetera, et cetera. That is something that we impose in the numerical work from the beginning. But there is this uniaxial anisotropy. Uniaxial because if I now look at this being the preferred axis, then some particles are moving up. Along that, some particles are moving down. So it is basically up-down arrows sitting next to each other, which is sort of like the kind of symmetry that you have in pneumatic liquid crystals, where you have these rod-like objects, but there is no distinction between the top and the bottom, the head and the foot. So one can basically use similar kind of analysis as one would do for a two-dimensional pneumatic, where one has a 2x2 matrix that one can construct from the directions of the velocities of the particles. So I've just written down there, it's something which is very standard. One diagonalizes this matrix and traceless matrix. So there is one positive and one negative eigenvalue. The positive eigenvalue tells you about the degree of this anisotropy. And then the corresponding eigenvector tells you about which is the preferred direction. So this can be done. I mean, from the velocities of a snapshot of the system, one can then look at the values of this lambda, which is the degree of an anisotropy, and the corresponding angle, which tells us about which direction this anisotropy is pointing. And then one has a large number of simulations. From that, one can get a distribution of this lambda and also a distribution of the angle, the preferred angle. And as you can see here, the distribution of this lambda peaks at a non-zero value, picks up an average value, of course, has to be positive, but it peaks at a non-zero value, which says that there is some preferred value of lambda. The distribution of this angle shows something that looks a little peculiar. It has peaks in the x and y directions. So the X and Y directions, where do they come from? This is basically coming from the simulation box. Simulation box is a square, so that has well-defined X and Y axis. And this picture will tell me that these streams, they are preferentially oriented one of those directions. So there is certainly some anisotropy because this peaks at a non-zero value, and this also shows a structure which is, in some sense, one could guess from the previous pictures. See here, the anisotropy long axis, I mean, the direction in which the correlations are maximum, pointing in along the y-axis. Here it is pointing in on the x-axis. So some effect of the boundary is present in this system. Of course, it's a finite system, so one has to understand, and it's just a finite size effect, or there is actually some preferred directions. So we looked at these distributions for two systems which are very system sizes that are very different from each other, and this is what we find, that for the distribution of lambda, if I look at two systems which are roughly 10 times, size is 10 times different, they get very similar distributions. And in particular, as I go to bigger system, the average value actually goes, increases by a small amount. So this suggests that if we go to still bigger systems, this kind of averages will be non-zero, and the value of, there will be a positive value of average value of lambda where the distribution peaks, which is certainly different from zero. And so this kind of anisotropy, you expect that to persist even in a big system. But the distribution of the angles looks somewhat different. Again, in the two system sizes, the blue one is for the smaller system size, and this brown one, or this one, is for the bigger system size. And there is certainly, these peaks are decreasing as you go to bigger and bigger systems. So if this preferred direction basically is tied to the your system, the directions that you have, I mean, the sample, the boundary conditions that you have used for the sample, then one expects that for large values of number of particles, this kind of dependence will probably will not be there. So this is what we suggested, that with increasing system size, this kind of preference for either the x-axis or the y-axis for these streams, that is decreasing, and it might go to zero. We have to do a little more work. I mean, look at other system sizes to see the systematics of that. But this preference for the x and y axis, this seems to decrease with increasing system size. So this is basically up to the point that we have characterized the complex flow that we have in this liquid. Another thing that we have looked at, we have maybe 5 minutes or something? Okay. So initially one starts with a situation where the velocities and the random forces, or the self-propulsion forces, are chosen entirely randomly, no correlations. But we saw that in the steady state, they develop these correlations. So as a function of time, the development of these correlations is basically something that, another problem that has been studied a great deal, which is basically ordering dynamics, formation and coarsening of order, as let's say you take a spin system and then you quench it from a high temperature to a temperature below the critical temperature, then one begins to see ordering in the system, and there is a length scale associated with that, which grows and so on and so forth. That has been studied quite extensively in the context of spin systems. So here also that kind of a coarsening, or this kind of a development of order takes place, that initially there was no correlation between the forces and no correlation among the forces or among the velocities, but this correlation is developing as a function of time. So one can study how the length scale associated with those correlations, how that is increasing as you go to longer and longer times. Again, the student has some preliminary data on that. Again, more work needs to be done. But if you see the development of the length scale, here you're looking at two different measures of this correlation length. It initially starts from a very small value, grows, and then in the steady state, of course, it becomes a constant. But this growth process, of course, I mean, here it is not growing very much. One has to characterize better, but from what we see till now, it looks like this growth process is very different from what you have when you have a spin model with the appropriate symmetry. That spin model is the two-dimensional XY model with net magnetization equal to 0, and that has been studied earlier also in the literature. So we find that this behavior is very different from what one finds there. There are other sort of more specialized things. Says that domain was rough in this situation, whatever. So so far, I mean, this is all that we have for understanding both the strange liquid phase that we get due to when the jam state melts due to activity, and also how these correlations develop as one starts from a completely uncorrelated situation, and how the system basically gets self-organized in this state. So pretty much my time is out. So this is basically the summary that I will not read it out. These are the main findings, that there is this velocity sorting or the growth of correlations. And then this is a new thing, that the self-organized state typically has two large streams flowing in opposite directions, and some things about the development of order in the system. At this point, I mean, it's all entirely numerical. We are trying to work out some, at least approximate analytic picture of why this kind of self-organization is happening, and the other things that one is seeing in the simulations. But just work in progress. So thank you for your attention.
A couple of questions. One is, do you know what happens if you study this on a sphere instead? Do you find, because the defect pattern for the nematic case and the polar vector case will be very different and be seen most clearly in the sphere, where you'll see +1, 2 +1 defects versus 4 halves. So do you know what happens? Have you looked at this?
I have no idea, but yeah, point is well
that might be a nice diagnostic. Then you would,
If this is sort of more like a pneumatic, then you will have different kind of.
Okay. Another quick point, which is that the velocity alignment itself is maybe not so surprising, because you've got particles which, on the one hand, each one wants to have a certain speed. On the other hand, they have a sort of generic repulsive interaction, which on large scales will make the system behave like it has a viscosity, which will align the velocities. So the mechanics of velocity, of producing coherent velocities, is essentially particles which pump themselves to have a non-zero speed and then want to make their velocities equal.
But I mean, the length scale associated with that alignment seems to become very long, and it's sort of
I think one can do a theory of that.
Yeah, so that would be very nice if one could actually understand that. And also the forces. I mean, I think the velocity alignment doesn't require sort of bodily motion of the particles. The particles can, through collisions, reorient their velocities and so on.
Right.
To get the force alignment, initially the particles which have sort of similar direction to the force are separated by large distances. So they sort of move through the whole system and then come together.
Right.
So that's, I think, it's a little more.
But I think we should talk a little.
Sorry, I had a question. Like, do you keep the density of particles constant?
Yes.
Okay.
Not a particles constant. It's all in a box, simulation box, fixed size. So the density, of course, is constant.
Okay, and this is probably, like some follow-up of something, this thing. So these long distance velocities, do you have some kind of effective, some fluctuating hydro or something for the theory of what you see in your numerics?
Sure. I mean, there are fluctuating hydrodynamic theories of liquid states of active particles. But I mean, this particular limit, where the persistence time is going to infinity, is a somewhat peculiar limit. So that has not been studied in great detail. One assumes that this active forces also are changing as a function of time over a time scale. So there are theories, and there are many interesting results that one gets from those theories. Sriram has been one who is pioneering these theories.
Okay, thank you.
So the average velocity of one tagged particle will be finite in the thermodynamic limit?
Yes. So average velocity, I mean, we didn't show that slide, but long time average velocity of a particle actually is in the same direction as average velocity is in the same direction as the constant active force that is acting on it.
So is the value around 0.5 or much less?
No, much less.
Okay.
Less, yeah. So I mean, our active force is in this unit it's 3. The average velocity will be 0.05 or something like that, of that order.